Welcome to MIT 307 Numerical Analysis class. In this lecture, we are going to introduce decomposition methods. First, why do we even care about matrix decompositions? Consider simple linear equations. This one, 18x is equal to 486. So here when we are dealing with this sort of equations, our intuition says divide both sides by 2. And then once we are done with dividing by 2, we will have 9x is equal to 243. Then we'll have 9x's here. So we continue dividing by 3 and then dividing by another 3. So this x will remain alone, and then we will simply obtain x this way. Okay, so this is sort of different approach to get the solutions instead of dividing both sides by 18, because dividing both sides by 18 looks kind of harder than dividing by 2 and 3 and 3 successively. Okay, so this way we say we factorize the number 18 as 2 times 3 times 3 first, and then perform easier divisions. For an analog of this idea to the system of linear equations, we consider ax equals b, and we assume a is equal to lu, such that L is a lower triangular and U is an upper triangular matrix. Then if we have this A is equal to LU, then we say AX equals B is equal to LUX is equal to B. And then we can rewrite this equation as LY is equal to B for Y, which is also equal to UX. Okay, and then we solve this part first. This can be the solution for that part can be found by forward substitution. And then once we have the value of y, we can put it there and solve for this system. And U is an upper triangular matrix, so we can find the solution by backward substitution. Okay, so several approaches exist to find such lower and upper triangular matrices. What we consider here is decomposition by Gaussian elimination, and Doolittle and Krauss methods, and Cholesky decomposition. Okay, also the decomposition methods are not just limited by the LU decomposition. It is not the only option. We can also talk about eigenvalue decomposition or singular value decomposition and so on. So there are various ways of decompositions. Just we choose the one which easily takes us to the target. Okay, so here we are trying to solve linear systems. So LU decomposition is a good candidate, good decomposition approach to work with. Okay, LU decomposition by Gaussian elimination is obtained by expressing this elimination with elementary matrices. Okay, so we start with the matrix A, and we convert this to an upper triangular matrix U by Gaussian elimination method. This way we obtain U naturally. So this will be the result of the Gaussian elimination. And then the elementary matrices to be used for this Gaussian elimination will be used specifically for the selection of the matrix L. For example, let a matrix A be converted to a matrix U by left multiplying the elementary matrices L1, L2, dots Lk respectively. Then we obtain this, so the equation will look like this. So we have A, and we multiply by L1, L2 dots Lk from the left to obtain U. Okay, then we can multiply this equation from the left by indeed L to the k inverse, L to the k minus 1 inverse, and so on until we get to the point there where we multiply by L1 inverse. Once we do that, we will obtain just A on the left, On the right, we will have some sort of matrix products. So we choose L is equal to the product of L1 inverse, L2 inverse, and so on, up to Lk inverse. This way we obtain matrix L and U. Okay, so here there's a quick remark that we are working with lower triangular matrices here because their elementary row, they will represent the elementary row operations, so they are lower triangular matrices. The inverses of lower triangular matrices are also lower triangular matrices, or the product of two lower triangular matrices are is also a lower triangular matrix. So this will give us that this product, indeed, this makes sense, and we can obtain the lower triangular matrices out of this computations. Okay, let's see this on an example. Multiply given A from the left by L1, L2, and L3 in the given order. So here we have the matrix A. So we need to eliminate, we're performing Gaussian elimination, so we need to eliminate this numbers because the leading coefficient is leading entry is 3 here in the first row. So the below this on the very same column, we shouldn't have any non-zero entry below this quantity. So we need to eliminate all of these numbers and make them 0. To that end, we multiply the first row by 1 and then add to the second row. And also we multiply the first row by -2 and then add the result to the third row. And multiply the first row by 3 and add the result to the third row. This way we can eliminate all these numbers and make them 0. So this is what really happens after multiplying L1 with A from the left. Okay, so this is copied down, and we are now done with the first column. The first row has leading entry 3, and below that all the numbers are 0. So we are moving on to the second row. On the second row, we need to multiply the second row by 5 and then add the result to the third row. So this is there. And also we multiply the second row by -8 and then add to the result to the fourth row, sorry. So this will be -8. Okay. So by multiplying L1A from the left by L2 will give us this matrix. So we are done with this column, and here we are done with this column. So we copy the matrix from here to there and say, okay, we need to eliminate this number from here, so this has to be 0. So for that end, we can multiply this matrix by -3. I mean the third row by -3 and add the result to the fourth row. This matrix, L3 matrix, will perform this row operation. So we multiply the matrix L2 L1A by L3 from the left, and this will give us the matrix U. So this matrix U is indeed upper triangular, right? And we already found the U naturally, so it's there. What about the matrix L? If we consider rewrite this equations, here we have L3 times L2 times L1 times A is equal to U. Then the matrix L for which A is equal to LU should be L is equal to L3 L2 L1 inverse. So we take their product and also inverse, so this will be equal to our matrix L. We start with finding the matrix L3 L2 L1. Okay, so this is L3 matrix, this is L2, and this is L1. So if we multiply them out, we obtain this matrix. Okay, this is not a coincidence, so we have the numbers here. So this very same entries with L3 matrix here, and there we again have the same thing, and also here it's the same. Okay, so this makes sense because we always whenever we multiply this sort of matrices in the given order, we obtain the same entries below. Okay, so this is something to note. Okay, then we can move on to finding the inverse. So this is our L1, L2, L3 matrix, right? So L1, L2, L3, L3, L2, L1 matrix is this one. And we know if we have lower triangular matrices uh, with diagonal entries being 1 on all the positions, then we say by theorem we can find the inverse of such matrix by replacing all the entries, all the off diagonal entries by their multiplicative, sorry, the additional inverse. So this will be -1, this will be 2, this will be -3. So this is what we get, and 5, -5, -8 to 8, and -3 will be 3. So this is our matrix L. Okay, now we are done because we were trying to find such matrices, L and U matrices, so that A is equal to LU. The U matrix is given here, so this is matrix U, and this will be the matrix L. If you multiply them out, so if you multiply L with U from the left, you will obtain A. Consider the matrix, okay, A. So this is the matrix, and we perform Gaussian elimination by starting with multiplying by L1, okay, to the matrix A. Okay, when we do that, we obtain this, and here there is one thing we check here. So we multiply A by this number, this matrix, and then we immediately write its inverse here. Okay, so this is the matrix and this is its inverse, because at the end of the day we will find L1 matrices, L1, L2, L3, whatever. I don't know how many of them will exist to arrive at the upper triangular matrices, but at the end of the day we will multiply them and then find the inverse. Okay, so our goal here is to take the inverse immediately at the same point. Okay, so say this is our L1 matrix and this will be our inverse. Okay, we note this L1 matrix to somewhere and move on to the next stage. Okay, so this is L2 matrix. Okay, this L2 matrix is multiplied by what we obtained after multiplying by L1, and then this will give us the upper triangular matrix, and we say L2 inverse is also here. Okay, so L2 inverse is found immediately at the very same point. Okay, so now we are ready to move on for finding L and U matrices, because L1 inverse is given here, L2 inverse is given there. So we can say L is equal to what? L1 inverse, L2 inverse. So L1 inverse times L2 inverse will give us the matrix L. So this way, if we note the inverse of the L matrix immediately at the same point, we don't have to multiply them and then find the inverse. We just perform the operations immediately at the very same point. Okay, so L1 inverse times L2 inverse will give us the matrix, the over triangular matrix L. This is another way to go about the problem, or you can also perform the same operations with finding L1, L2, L3 matrices. But this way, if you follow this way, you, for example, found L1 matrix and then its inverse, and in the next step you'll work with L2 matrix and its inverse. Once we have this, the L1 inverse and L2 inverse, we can proceed by multiplying these two and then saving some memory, right? Because if you wait until the end, you have to store all the L matrices, which is kind of tedious, because they will all take some space on the storage, on the memory. So if you follow this idea, this will immediately give us the inverse, and we can multiply these two and then forget about them forever. Okay, so in the next step, say we have L3 inverse, we multiply L3 inverse with the previous matrix, which is representing L1 inverse, L2 inverse, and then we forget about all L1, L2, L3 matrices, and we just store the product of all these matrices. Okay, the inverse of these matrices. This way we can save some space. Okay, next we consider Doolittle and crowd decompositions. Doolittles and crowd decompositions are also LU decompositions. Doolittle decomposition assumes ones on the diagonal of the lower diagonal L, while crowd's approach requires the same for matrix U. Okay, so if you consider LU decompositions of A here and there, so this will be Doolittle, because here we have the ones on the diagonal of the lower triangular matrix, and the crowd approach we will have ones on the diagonal of the upper triangular matrix. So this is the difference between these two. First, let's consider the Doolittle decomposition. Okay, say this is our matrix A11 to ANN. All the entries are given, and we have the Doolittle decomposition. So lower triangular matrix will have ones on the diagonal entries. Okay, so these are the ones, and upper triangular matrix will be just an arbitrary upper triangular matrix. Okay, so here we have ones. This will help us finding all the other entries. We are also given this matrix, so we know all A11 and ANN, all the entries of the matrix A is given, because we are decomposing the matrix A, so it must be given before we even start talking about area decomposition. Okay, multiplying the first row of L, so the first row of L with the columns of U. So the first row of L is here. If we multiply this by the columns of U, then we obtain, if you consider the very first one, we'll have U11 here, right? Because we have zeros there, all zeros. So even if we multiply this with the other entries besides the first one, we will still obtain zeros. Okay, so this will give us U11 is equal to A11. Then we move on and multiply by the second column. So again, 1 is here and the rest of the entries are 0. So if you multiply the first row with the second column, we will obtain U12 alone. Okay, U12 will be equal to A12. So this is here. This way we can obtain the first row of the upper triangular matrix. So the first row can be found this way. Okay, let's perform the same thing on the last column. So again, 1 is here and all the other entries are 0. So this will be 0. This part will be 0. So U1n will be equal to A1n. Okay, so this is what we obtain. Okay, now seems like we are done with finding the first row of the upper triangular matrix. Okay, so this is found. Now we can proceed and multiply L with the first column of U. Okay, so if you multiply the whole matrix with the first column, then this will give us, okay, so this times that will give us A21, right? So the second row with the first column will give us A21, right? So here we have zeros there, and L21 times U11 will be equal to A21. Okay, so this means L21 is equal to A21 divided by U11. Okay, so this is here. And also, if you multiply the next one with the this one again, right? So then L31 will be L31 times U11 will be equal to what? A31. So we can write L31 as A31 divided by U11. Okay, so we're basically multiplying all the rows with all the rows of the matrix L with the first column of the matrix U. This way we can obtain all the entries of the first column of the on the lower triangular matrix. Okay, so this way we obtain all the numbers here, and also we obtained all the numbers there. So this will leave us with, okay, so here these are also known and these are also known. Okay, so this way we obtain all the numbers here and there. So the first columns and first rows are done. We have the entries. Okay, so we can proceed to the next step and we perform this very same thing. Okay, so we can proceed and say let's multiply the second row with the columns of the U, and then obtain what here the general formalization is here, so we can follow the same pattern for I is equal to 2 to from I is equal to 2 to n, and then from j is equal to 2 to n, and this will give us AU1 AUJ will sorry UIJ will be equal to AIJ minus sum of k's from 1 to I minus 1 Lik times Ukj. Okay, so this will give us Uij values, and for the lower triangular matrix we can perform this computation, and this will give us the entries on the matrix. Okay, so this is what we really have. Okay, let's see this on an example. We multiply the first row with the columns of the upper triangular matrix. Then we'll have U11 is equal to 5, and also U21 will be equal to 4, and U13 will be equal to 1, right? Because this times that will give us indeed U21, and this is equal to 4, and here we will obtain U13, which is equal to 1. Okay, so now once we are done with the first row of the upper triangular matrix, we can put their values here on the upper triangular matrix, and then we multiply the second row of the lower triangular matrix by the first column of the upper triangular. Then this will give us 5 times L21 is equal to 10. So this will give us L21 is equal to 2. Okay, again multiplying this row with that with this column, we obtain 5 times L31 is equal to 10. This will give us L31 is equal to 2. Okay, so we substitute all these numbers on the corresponding entries and then move on. So this will give us this matrices, and then here we multiply the second row with the second column. So this will give us 8 plus U22, right? So 8 plus U22 is equal to what? 9. Okay, so 8 plus U22 is equal to 9 gives us U22 is equal to 1. Okay, so again multiplying this by the third column, we have 2 plus U23 is equal to 4. So U23 will be equal to 2. So we substitute these numbers on the upper triangular matrix, and then we move on. So here we multiply this row by, for example, with this column. This way we have 8 plus L3 2 is equal to 13. So this will give us L3 2 is equal to 5. Okay, so we are also done with that number. So here the only unknown is here, so we can multiply the last row with the last column. So this will give us 4 plus 2 plus 10 12 12 u12 plus u33 is equal to 15, so u33 will be equal to 3. So this will give us the LU decomposition of the matrix A. Okay, for the crowd decomposition, we again start with the same matrix, but this time we will have ones on the upper triangular matrix, on the diagonal of the upper triangular matrix, multiplying L with the first column of U. So here, when we do that, when we multiply all the rows with the first column, we will have L11 is equal to A11, right? So L21 is equal to A21, and Ln1 is equal to An1. So this is immediate the results in our immediate results. So we can obtain all of these quantities, and then we can move on and say, okay, multiply the first row of L. Let's clean this. First row of L with the columns of U. Okay, so we know L11 is equal to A11, right? This is something we have found. So we can multiply the first row with the, for example, second column. Okay, when we do that, we will have L11, which is also equal to A11. A11 times U12 will be equal to A12. So this will give us U12 is equal to A12 divided by L11. Okay, so the same thing for the next column, and for the last column we will obtain what? U1n is equal to A1n divided by A11. Also L11, so which are the same, because L11 is equal to A11. Okay, so once we obtain all the numbers, this numbers, so here we have found this numbers, these entries and that entries. From that point on, we can we can follow the same pattern and obtain the rest of the entries as well. Okay, so following the same fashion, for I is equal to 2 to n and j is equal to 2 to n, we obtain the entries of lower triangular matrix by this formulation, and upper triangular matrix, the entries of upper triangular matrix by this formulation. Okay, so an example, this is matrix A, and we want to write it as LU matrix, the product of L times U. So this is L and U. On the U we have the diagonal entries being 1. So if you multiply the rows of the first with the L matrix with the first column, we obtain L11 is equal to 5, L21 is equal to 10, and L31 is equal to 10. So this is something we can find immediately. So here the numbers will we substitute the known numbers here on the matrix, and then we can, okay, let's eliminate this. We can multiply the first row with the columns of the upper triangular matrix. Then this way we will have 5 times U12 is equal to 4, so U12 will be 4/5. And here we have 5 times U13 is equal to 1, so U13 will be 1/5. Okay, we substitute these numbers there, and we move on to the second column of the lower triangular. Okay, so here we can multiply, for example, this by the second row with the second column. So this will give us 8 plus L22 is equal to 9. So L22 will be 1. Okay, so multiplying this third row with the second column, we obtain again 8 plus L32 is equal to what? 4, is it? We multiply this by that, so this will give us okay, so 8 here, so this, right? So the third row with second column will give us this entry, so it will be 8 plus L32, and this makes L32 equals 5. Okay, so this is what we obtain for L32 and L22, so we substitute their values here. Okay, here we have U23, so we need to find them. So we can multiply this row with this column. Okay, so then we will have 2 plus U23 is equal to 4. Okay, so this will give us U23 is equal to 2. We substitute this number here. And also we are left with L33, so this is the last unknown. We can multiply the last row with the last column. Then this would give us 2 plus 10, so 12. 12 plus 3 will give us 15. So L33 is 3. So we have found the lower triangular and upper triangular matrix by crowd decomposition as well. Okay, Cholesky decomposition. Let's start with the definition. N by n symmetric matrix A is positive definite if and only if for any non-zero vector x transpose AX is greater than 0. Okay, so then we call this matrix as positive definite. Okay, for any given x, non-zero, for of course it has to be non-zero. If we say x transpose AX is greater than 0, this will return us some number, because x is 1 by 3, 3 by 1, so transpose will be 1 by 3. So this is 3 by 3 for example, if we consider 3 dimensions matrices. So this will give us 3 by 3, and this will be 3 by 1. So if we multiply them out, we end up with 1 by 1 matrix, which is a real number. So this can be makes sense. Okay, so for any dimension you can still do the same thing, and this will make sense. Okay, so if the matrix A satisfies this condition and it is symmetric matrix, then we say A is positive definite. Another definition, the Cholesky decomposition of a positive definite matrix A. So the Cholesky decomposition is only for positive definite matrices. Okay, so this is a remark to put here. This is a decomposition. The Cholesky decomposition is a decomposition of positive definite matrices, and it is in the form A is equal to L times L transpose. Okay, so our this is again a new decomposition, but the upper triangular matrix will be the transpose of the lower triangular matrix, where L is upper triangular with positive diagonal entries. This is again important because you'll see we can come up with the positive and negative diagonal entries on the process when we are trying to find when we're trying to find Cholesky decomposition. So we assume that the diagonal entries are positive. Okay, so this will be our assumption. Okay, so an algorithm, consider the following matrix for Cholesky decomposition. So this will be the lower triangular matrix, and its transpose will be our upper triangular matrix. And here we assume A is a symmetric positive definite matrix. Okay, diagonal entries can be found by, for example, if you consider the first row with the first column, if you multiply them out, you will see L11 squared is equal to A11. So this will give us L11 is equal to square root of A. And of course, this will be positive. If you don't have the assumption that the diagonal entries must be positive, then L11 could have been negative root A11 as well. Okay, so for this reason we say the diagonal entries are positive. Okay, so L11 will be root A11, and also here we let's eliminate this rectangles. And once we have L11 and L22, sorry, L11 here and there, we can multiply them. For example, we can multiply the first row with the columns of the second matrix. Okay, this way we can find, for example, L21, L23, sorry, L31, L34, and so on. So up until we have Ln1. So these are how we can find the other entries. If we have these entries, they are the same with that, so we are done. So this is nice, good news, because if you know the rows of the upper triangular, you already know the columns of the lower triangle, because they are the transposes of one another. So if you follow this algorithm, we can obtain all the entries. Okay, let's see this on an example. So this is our matrix. This is symmetric positive definite matrix. If it wasn't, then we would have some issues while finding the Cholesky decomposition. Okay, so this is also a way to, if you can find the Cholesky decomposition, also it says this is a symmetric positive matrix. Okay, so it is symmetric. We can easily check that. So 15 is here and there. So this is the mirror reflection of the diagonal, right? So this is symmetric. Positive definite. It's also the positive definite, but we are not here to check that. We just find Cholesky decomposition and believe it is positive definite. Okay, so we have the lower triangular matrix and its transpose as the upper triangular matrix. We multiply them out, so L11 squared will be equal to 25, so L11 will be 5. This is the first thing to do. Okay, so once we have the number 5, we can, for example, multiply the rows of the first matrix with the column of the first column of the second matrix. Then this will give us, for example, L21. Like 5 times L21 will be equal to 15, so L21 will be 3. And here 5 times L31 is equal to negative 5, so L31 will be negative 1. So this way we obtain those numbers, and those numbers can be substituted in both matrices because they are transposes of one another. So we substitute these numbers here and there. They are already found, and we can move on to the other unknowns. Okay, now we can, for example, multiply the second row with the second column. This way we have 9 plus L22 squared, which is equal to 18. So L22 squared will be 9, so L22 will be 3. Okay, because it is positive. So we put 3 there. Okay, and then we move on to the next unknown, 3 to 1. Sorry, 3 L32. So here we multiply the second row with the third column. then this will give us -3 plus 3 times L32, right? So also this will be equal to 0, so L32 will be +1. Okay, so we substitute the L32 also here. So we are at this point, the only unknown is L33. So we multiply the this this row with the last column. So the last row with the last column. So this will be +1 plus another one. This will be 2. 2 plus L33 squared is 11. So L33 squared will be 9. So L33 will be equal to 3. So this is the Chomsky decomposition of the given matrix. That's all for today. Thanks for watching carefully. Bye.